Now that we've spoken a little bit about what happens to sample means when the sample size gets bigger, we can continue talking about sampling distributions. The central limit theorem will guide how we answer different types of questions. Imagine in this case that you have random samples from two populations. Some samples, which we'll denote by x1 all the way up to xn, from a population with mean mu1 and variance sigma 1 squared, and some other observations that have been sampled from another distribution independently of the sampling from the first distribution. We call them y1 all the way to ym. They come from a distribution with mean mu2 and variance sigma 2 squared. Now you compute the sample mean for both of these samples, x bar and y bar. If you're interested in determining whether there's a difference between these two means, whether x bar and y bar are in fact different, then you will compute the funny standardized quotient here. X bar minus y bar, might as well put those between brackets here to help you recognize that we're talking about a quantity that could be zero if the sample means are the same, minus mu1 minus mu2 divided by something that plays the role of the standard deviation. This is a pooled standard deviation. And this, as a coefficient, will have, according to something like the central limit theorem, will have a standard normal distribution when the number of observations in each sample goes to infinity. And so this is a limiting result in the same way that the central limit theorem. One thing to notice, when I say that these samples come from two different distributions, what I mean is that they're being sampled independently of one another from distributions. It could conceivably be the case that you do a first sample from a distribution, and then independently of that, you take a second sample from the same distribution. That would also apply here. In this case, mu1 and mu2 would both be the same, and sigma 1 squared and sigma 2 squared would both be the same. So as an example, we'll imagine that you're looking at two different box filling machines. These box filling machines are used to fill cereal boxes on assembly lines. So the boxes go down the line, and whenever they come under the spout, whatever, a bunch of Raisin Bran comes down and fills the box. What you're trying to measure here is the weight of the product in the boxes. The machines are designed so that they always release the same weight of cereal, but in practice, I mean, these are discrete objects, and each flake of a cereal doesn't weigh exactly quite the same as the other one. There's variation in the baking process, and there's also variation in how they fit together in the space that they're supposed to fill before they get dropped into the cereal box. So we would expect that there would never be quite exactly the same amount of cereal weight-wise being dropped by the machines. Let's assume that we know that in both cases, the variance of the weights is 1. So we'll take a sample of 36 boxes from each of the machines, hence this is done independently, right? We're picking it from different boxes, and then you report the weights. What's the probability that the difference between the sample means is less than 0.2, assuming that the true means are identical, assuming that, in theory, the machines are calibrated to give you exactly the same amount of cereal in the boxes. In that case, what we have is that the means are the same. mu1 is equal to mu2. We don't know what the values are here. We have sigma 1 squared, sigma 2 squared being 1, and the sample size is 36. So we are interested in the probability that the difference between the samples would be less than 0.2, but we don't know necessarily which one would be larger. Is it x bar? Is it y bar? We don't know. We just want the difference to be less than 0.2. So this can be written using absolute value notation, and if you do the expansion of this expression, you will get that x bar minus y bar has to fall between minus 0.2 and 0.2. You standardize the quantity x bar minus y bar according to the results, the theorem of the difference of sample means, And so you have to apply the same operation to all the sides of the inequality here. So we subtract 0, which is mu1 minus mu2, which is what we assume the difference will be because the machines are calibrated to have the same mean, and we divide by the pooled standard deviation. So that was sigma 1 squared divided by n plus sigma 2 squared divided by m, and you take the square root of this, so 1 for the sigma squares divided by 36 because they have the same, because both samples have the same size. And then if you evaluate these quantities, well, this is exactly z. This value here numerically would be minus 0.8485. The other one would be 0.8485. So what you're interested in computing is the probability that the standard normal falls between minus 0.8485 and 0.8485, this area here. And you do it by computing phi at 0.8485 first, so it gives you the full area from infinity to 0.8485, and you remove the tail here. So this is this expression that we've seen before, just with different values here. Go to the table, go to R, and you will get that this probability is about 0.6. Now I wrote equality here, but this is a limiting result. You only have equality in the limit when n and m have both gone to infinity, and this isn't what we have here. N and m are resolutely finite. This is an approximation. So there's 60% chance that your sample means will be within 0.2 units of weight from one another, given that the variance for each machine is 1. We also have sampling distribution information about the sample variance. If you have a sample, x1 to xn, you can compute its sample variance. It is going to be the sum of the squares of the differences between the observation and the sample mean divided by n minus 1. Here, you are not dividing by n, the total number of observations in your sample, because you have lost 1 degree of freedom. You've used the values of the sample to compute the sample mean. You would only divide by n if here instead you had the true mean and you knew what it was. Right? So what this is saying is that what we're computing here, s squared, isn't quite the same as this quantity, the true variance. You can only compute this when you know the true mean. When you use the sample to estimate the true mean, the expectation, when you compute the sample mean, you have lost 1 degree of freedom. You've already used your sample to do one computation, and it's too taxing to believe that you haven't lost some information by doing so. And so we lose 1 degree of freedom. This denominator here would be the number of observations in the sample minus the degrees of freedom that have been lost by estimating other quantities along the way. So that's the variance of your random sample of size n. Assuming you take it from a normal population with variance sigma squared, not always guaranteed, but in this case this is what we assume, the statistic chi-squared, which is going to be n minus 1 times s squared, so that has the effect of canceling the denominator, divided by sigma squared, should follow a chi-squared distribution with n minus 1 degrees of freedom. We call this quantity here nu. And this chi-squared with mu degrees of freedom, chi-squared is a special case of the gamma distribution, where the first parameter is exactly 1/2, and the second parameter is nu. You can expand the chi-squared statistic here. It is going to be the summation of the differences between the observation xi and the sample mean squared divided by the variance sigma squared. So this plays the role of the standardized quantity. This plays the role of z. Right? When you're trying to do these probability computations, on the difference of the means or on the actual sample mean itself. On a standardized quantity, you end up, looking at things like this as an approximation for some other thing you were interested in computing. Well, when it comes to the sample variance, Z is often played by this chi-squared quantity that you'll have computed here. This is what the distribution looks like in general. Here I'm giving you chi-squared with 8 degrees of freedom. So that would be the distribution you would use if you had a sample of size 9. And the actual values are given in tables that will be made available to you. You can also compute them using R and other statistical software. And the quantities of interest, the probability that your X would be smaller than some threshold X. So if you're interested in computing this quantity here, you can look at what it would be by looking at the critical values. The critical values are those values on the x-axis that make it so that the area underneath the curve from that point onwards is equal to alpha. So if you're looking, for instance, at chi-squared 0.05 with 8 degrees of freedom, you're looking for the point on the x-axis for which the chi-squared distribution with 8 degrees of freedom has area 0.05 from that point onwards, or in other words, for which this area here is 0.95. And what that value would be, well, you look it up by the number of degrees of freedom, 8 in this case, and you're computing for alpha 0.05, this value here, about 15.51. What this is telling us is that the integral between 15.51 and infinity of the chi-squared distribution, 8 degrees of freedom, with respect to x, 0.05. Well, I wrote here the integral of the chi-squared distribution with 8 degrees of freedom. This is the name of the distribution. What I really need is the probability density function that corresponds to that. And then we'd have to go back to what the PDF for the gamma distribution is, and you'll see it here. It's this expression right here, where you replace the first parameter in the gamma distribution by 1/2. Okay. You'll never have to integrate this directly, and you'll rarely see this showing up. You'll just need to find these critical values, and you need to remember how they're defined. You need to remember that it's the point after which the area under the curve is equal to some quantity alpha. We're going to meet this concept very often, especially in the following sections. Formally, this is what I've described to you here. If you pick some alpha value between 0 and 1 and some number, which is the degrees of freedom, then chi-squared alpha at nu, that's the critical value. That's the point where the area underneath the chi-squared PDF from that point onwards is greater than alpha. That also means that the probability of drawing a value from the chi-squared distribution with nu degrees of freedom, which will be larger than the critical value, is alpha. So if you had nu equals 7 and alpha equals 95%, then the critical value of the chi-squared distribution with 7 degrees of freedom at 0.95 is 2.167. 7, alpha is 0.95, this is where you are, 2.167. What this is saying is in the chi-squared distribution with 7 degrees of freedom, this is the point, roughly speaking, after which 95% of the area is found. In the central limit theorem, when you compute your standardized value z, it is assumed that you know what the true variance of the underlying distribution is, right? Because you're dividing by the square root of sigma squared over n. But what happens if you do not actually know what the population variance is? In that case, you will try to estimate it using the sample variance. But when you estimate using the sample variance, you don't necessarily have the true variance. And so you've lost a degree of freedom again. Let's assume for now that you have a standard normal variable z, and some other variable v, which follows a chi-squared distribution with new degrees of freedom. If your z and your v are independent from one another, then the distribution of the random variable t, which is basically another standardization on z, so you take z divided by the square root of v divided by nu, this is going to follow what we call a student t distribution with new degrees of freedom. We'll basically say here that t follows a t nu distribution. Important uppercase, lowercase. This is a new distribution which we haven't seen before. It's a distribution which has the following probability density function. It is derived from the gamma function. Why is that distribution important? Well, when you do not know the underlying standard deviation or the underlying variance of the distribution, you estimate it, as I said, with the sample variance. And when you do so, you lose some information. So instead of computing the standardization x minus mu divided by sigma divided by square root of n, you're going to replace that by the sample variance. And here, instead of following a standard normal distribution, this quantity will follow a student t distribution with n minus 1 degrees of freedom. So whereas before we were often interested in computing quantities that look like these, and we said, you know, if we know the underlying distribution, this might be equal to some computation of probabilities involving the standard normal. But if you do not know the standard deviation of the underlying distribution, instead of using the z variable, you'll be using the t variable, which is obtained by estimating the sample variance. And in order to be able to compute these quantities, you need to know what the PDF is for the student t distribution. You need to know how to compute the critical values. Well, you can do so with the help of a t table, right? So the critical value for the t distribution with n degrees of freedom at a value of alpha, that's the point above which the area underneath the curve is equal to alpha. In other words, that's the probability that t being greater than the critical value is equal to alpha. Assuming, of course, here that t follows a t distribution with n degrees of freedom. It looks an awful lot like this expression, where we've replaced the chi-squared by t's. And it's not surprising that it looks like the same expression. It's the same concept, except here we're using a different distribution. One property that the student t distribution has that the other distribution didn't have, the chi-squared. Chi-squared is not symmetrical. It can only take on positive values. But the t distribution is symmetrical. So if you find this point here, critical value for a t distribution with a certain number of degrees of freedom, let's pretend that this is the right one, this area will have the same value. And this point here would be t1 minus alpha with r degrees of freedom. So once you found one, it's easy to find the other one, right? Because this number would just be minus times the original number, reflection in this axis. And you just need to know how to read the table. So what's the point after which the area under the curve is equal to, say, I don't know, 5%? If you have 3 degrees of freedom, well, you go into the 3 degree of freedom row and you find the value that corresponds to 5%, 2.353. So if this was the t distribution with 3 degrees of freedom, this value here would be 2.353, and the area under the curve would be 5%. One thing I want to emphasize is that the number nu here, the degrees of freedom, is the number of observations minus 1, right? You're losing 1 degree of freedom because you have used your sample to estimate extra parameters along the way. In practice, this is what you should be using. Like, what are the odds that you know what the true underlying distribution parameters would be, right? I mean, you've you've had to estimate that at some point in the past. You might as well continuously estimate it. If your sample is large enough, this isn't going to be a huge problem. When n becomes very large, the t distribution resembles the standard normal distribution. Well, if you have a t value which follows a student distribution with new degrees of freedom, and you pick any alpha between 0 and 1, this is the type of computation you might be asked to do, right? The area under the student t distribution between two symmetrically opposed points. Let's assume that this is symmetrical here. So this would be t alpha 2 mu and minus t alpha 2 mu. We pick this because it means that the area here is alpha over 2, and this area here is alpha over 2 as well, which means that since the area underneath the curve has to be equal to 1, the area under the curve between these 2 points has to be equal to 1 minus alpha. And if you do the sum, alpha 2 plus alpha 2 is alpha, plus 1 minus alpha, that's equal to 1. Yes, okay. So the area here underneath the curve between these 2 points is going to be the same as the area from minus infinity to this point minus the area from minus infinity to this point. We've seen this before, right? This is how you compute the area, and then you can work out what that's going to look like mathematically. That would be 1 minus the probability that t is greater than the critical value minus 1 minus the probability that t is greater than the other critical value, the negative 1. And work it out, you will get 1 minus alpha. What this is saying is that the probability in this case that x bar minus mu divided by the estimate of the sample variance s divided by the square root of the number of observations falling between the two critical points, minus t alpha divided by 2 with n minus 1 degrees of freedom, and t alpha divided by 2 with n minus 1 degrees of freedom, is going to be equal to 1 minus alpha. This is how you would make computations related to the sample mean when you do not know what the underlying sample variance is. As I've mentioned here, when the number of degrees of freedom increases, when it goes to infinity, the student distribution goes to the standard normal. When you increase the size of your sample, you would expect the sample variance to approach true variance. S gets better at estimating sigma when you increase the number of observations in the sample. From the table, for example, you could see that the probability when mu is equal to 8 that your distribution would draw a number greater than 2.306 is 0.025. Where do we see that? You go to the table, 8 degrees of freedom. This is given in the problem. And you're looking for probability here, or the point. You're looking for the critical value here where the area under the curve is equal to 0.025. This value is at 2.306. So the probability that your distribution would spew out a number greater than 2.306 if the quantities followed a student t with 8 degrees of freedom would be very small, about 2.5%. And what you get from this is that the probability that it would spew out a value smaller than minus 2.306 would also be 25%. So you know what the critical value is, 2.306 minus 2.306, and the probability that a student random variable with 8 degrees of freedom would take on values between minus 2.306 and 2.306 should be fairly large. In fact, we can compute what it should be. It should be 95%. So you've already found the critical points where you have 2.5% and 2.5%. This computation here is important. Not so much the 8 degrees of freedom bit, but being able to find the critical point for the 2.5% values and knowing how to compute these things to get the 95%, that's going to be something we'll do very often. Same thing will be true for the 99% here. and replacing this by what the quantity is required to be able to get 99%, 0.005, right? So this is something we'll need to be able to compute when we do confidence intervals and hypothesis testing. There's another distribution we will eventually use, the F distributions. So here we're talking about quotients of chi-squared distributions. So if you have a random variable u which follows a chi-squared distribution with nu1 degrees of freedom and an independent random variable v, independent from u, which follows a chi-squared distribution with nu2 degrees of freedom, then the distribution of the quotient u divided by nu1 and v divided by nu2 follows what we call an F distribution with nu1 and nu2 degrees of freedom. And typically speaking, we would write this as saying that F follows an F distribution with parameters nu1 and nu2. This is yet another probability distribution, and there's like infinitely many of them. We just talked about a few of them when we talked about continuous distributions, but the ones we talked about were not the actual important ones when the time comes to be able to do confidence intervals, hypothesis testing, and regression analysis. And for those, we need more interesting distributions like the T distributions, the chi-squared distribution, and the F distribution. This is what its probability density function looks like. So you see that it is again an offshoot of the gamma function. Not surprising because it is a quotient of chi-squared distributions, and the chi-squared distributions are themselves offshoots of the gamma distribution. There are tables again, and you compute them or you play with them the same way you would play with all of them. Very often you need to find the critical points and then do probability computations with them. In the literature, you will often find the first parameter, nu1 or r1 in this table, being called the numerator degrees of freedom. It's the one that shows up here, numerator of this quotient. And nu2, r2, that's the denominator degrees of freedom. Once you know what the degrees of freedom, both above and below, you go to these tables, and based on various values of alpha, you can find the probabilities of interest to you. The probability that f would be smaller than this quantity that you selected, and where you would have to be to make this happen. And this is important, especially when you're working with samples that come from different populations, and you've taken different sizes of samples from each population. It also works, of course, if you use samples from the same population with the same size. It's just a lot of what we show here will reduce to something we've seen before. S1 squared divided by sigma 1 squared, we know that this follows a chi-squared distribution with n-1 degrees of freedom. S2 squared divided by sigma 2 squared, we know that this follows a chi2 squared with m-1 degrees of freedom. Just get back to it here, this bit. Well, this quotient follows an F distribution with nu1 and nu2 degrees of freedom, when nu1 is n-1 and nu2 is m-1. So you can find your critical values in quite the same way. I'm not going to give you much of an example here, but this is something you should be able to read. You should find the critical value of the F distribution for various values of alpha and for various combination of degrees of freedom.